we're going to talk about today about how you can definitely win the lottery, or maybe. What should you do if you're playing some game of chance and you have to abandon the game before it's finished? How should you divide up the prize, the kitty that you've agreed on?
There was actually an instance in Monte Carlo in 1913 when the ball fell in black on a roulette wheel 26 times in a row, which is 66.6 million to 1 to happen. Hello and welcome to a brand new podcast from Gresham College. My name is Richard Taverner and I'm your host of Any Further Questions. This is a podcast where we invite one of our speakers on to go a little bit further on one of their recent talks. Today I'm joined by our current Professor of Geometry, Sarah Hart. Sarah, welcome. How are you?
Oh, I'm good, thanks. Thanks for having me.
Lottery winning maths. It's part of this year's series, Maths and Money. Can you explain a bit about why you chose to lecture on this particular topic, how you came up with the title of the series, and why you chose it?
So I think I like to explore the places where mathematical ideas bump up against life. But for me, a big part of that has been in the first 2 years, I've talked about maths and how it relates to our cultural lives, music and art and literature, and that's where the book came out of my talks on literature, really. And these are things that, they're cultural things, and a sort of an extension of that. What do we do with our time? If we're reading books, we're listening to music, but we're playing games, and we like to play the lottery, and that's part of, a fun recreational thing. And it should be fun, if you're gambling and it's not fun, then stop, right? But the lottery is a bit of fun thing that many of us do, and it does, in Britain anyway, it does fund some of these artistic endeavours that I've talked about in previous lectures. So I felt Maths and Money is quite an entertaining theme, and I've talked about lots of different aspects during those lectures. So that the one we're going to talk about today about is how you can definitely win the lottery, or maybe. But I've also spoken about game theory, which is kind of the strategies that can be used to do with money, like what's the best way to bid at an auction, those kind of questions that there is mathematics behind. And the very first lecture in the series was about actually physical money, like why are coins round? How do we divide our money up, our currencies? What's the basis of currencies? So those kind of very fundamental questions really about physical money lead to some really interesting mathematical ideas. So again, it's about what you have in your hand, what you're looking at, why things are the way they are, and mathematics has a lot to say.
They were fantastic. I've watched all three of them, obviously, and I do implore you to, if you're listening to this, I do implore you to watch them if you haven't already. I was talking to you before we started recording about probability, and about that is basically fundamentally the principles behind the lottery, and how the lottery functions is based on the mathematics of probability. So do you want to talk a bit about that and sort of how that comes to be?
So if you want to know, what are my odds of winning the lottery, you come straight to probability. Because probability is all about how likely or not events are to happen. And this could be anything from games that we play, throwing dice, tossing coins, certain kinds of card games. There is chance involved. Where there's chance involved, that's when you get to questions of probability. And on a kind of broader way, if you're looking at questions of how to understand large amounts of data and information, so that's statistics really, but you can use that large amount of data to then ask questions about, well, given all of this stuff that we know, all of this, for example, information about, how often it rains, something like this, we can gather data about that, but then we can use the ideas of probability, which we'll talk about a little bit, I'm sure, to work out actually, yes, what is the chance that it's going to rain today? Because it's not data that's already happened, it's a prediction about the future, and we can make those predictions using ideas of probability, really.
A lot of people believe that numbers that have come up before are less likely to come up again. And I did a bit of research, and I found a study in 1991 done by a few scientists, that Klopfelter and Cook, who discovered that numbers that had won the lottery, so numbers that had come up before, for 3 months afterwards, people avoided them and thought, I'm not going to use those numbers. They've come up before. They're not to come up again. I will do different numbers. It's an interesting way of thinking, and it's humans applying false logic to something which is not actually true. Talk a bit about that and why is it that we think in that way when we approach something like the lottery?
Yeah, so this is a common misunderstanding of people who play games of chance. The gambler's fallacy of thinking, I've tossed a coin and it's come up heads 10 times in a row, so the next it's got to be tails this time. We're overdue to have this thing. And you could have the same thinking about the lottery, where you say, okay, you can look at, the number 6 came up this week, so I'm not going to put 6 again next time. I also was speaking to someone who said that they always get the computer to choose their lottery numbers. You can get it. You can when you buy a lottery ticket, you can say, I'm just going to get the machine to pick for me. And they said, I do that because after all, it's a machine that picks the winning numbers. So it's more likely to choose it in the same way that the machine is. Again, so all these little thoughts or superstitions. The one about, yes, if a number's come up, it's not going to come up again. It's a natural thing to think, because what's happening there is you're aware that each number is chosen randomly, and so over a very long time you sort of expect the numbers to all come up with the same frequency, roughly. But the misconception is that somehow that should be resolved like straight away. So, if you toss a coin and it's heads, we know that heads comes up about half the time on average. So, but it doesn't mean that the very next coin you toss will be tails, because it's supposed to be one head and one tail. That's over the very long term. The probability, the rules of probability will say that over a long period of time it should be roughly half and half, because it's assuming a fair coin. But the coin doesn't remember what it's done, and this is where it goes wrong. So with the lottery balls as well, the lottery balls do not have a memory. They don't go, oh, well, it wouldn't be fair to have 6 again this week because we had 6 last week.
That's the fundamental key difference, is because humans have memories, and machines don't.
Exactly.
And we remember what came up last time, but to the machine, they could be starting it from the first time.
Absolutely.
Ever.
Absolutely. So this, memory versus lack of memory is the entire thing. And as humans, because we do remember, we can be tricked into thinking, oh, well, we're overdue for this number. We can't have 10 heads in a row. But these things can happen. They can happen. And at any given moment, the past is forgotten. Except by us humans who are watching. But we're not the ones, making the coin do or the dice roll in a certain way. So if you assume that, it's fair, it's random, these things are really random, if you toss a coin 6 times and you get heads 6 times in a row, the next time you toss that coin, you have a 50% chance of getting a head still, and a 50% chance of getting a tail. Now, if you tossed a coin 1,000,000 times and it was heads every time, you might start to question whether that coin really is an unbiased coin.
Yeah.
But, assuming that these things are, it's the same chance.
And we're not just getting it wrong today, we've been getting it wrong for centuries. And there have been, as you touched upon in your lecture, there have been mathematicians, very distinguished mathematicians, very clever people who have got this wrong, and they haven't realised they've got it wrong. But the reason they've got it wrong is because of one sort of glaring error. I wanted to sort of go back to sort of that time, and it all started with a man called Antoine Gombeau.
Yes.
Am I pronouncing it correctly?
Yes, you are. Yeah.
Antoine Gombeau. Could you tell me a bit about him and why he is where we start with the story of probability?
Yeah, so Gombeau, he enjoyed gambling. So he was a gentleman. He actually went by the nickname the Chevalier de la Mairie, even though it's no evidence that he was any kind of nobleman or knight, but somehow he became known by this moniker. But his real name was Gombeau, and so he was not exactly a professional gambler, but he did make money from gambling. And one of his games that he would play, or he would challenge people. Okay, let's roll a die, and I win if I can get a 6 at least once in the first 4 throws. So give me 4 goes to throw a 6. If I manage it in that time, I win. If I don't, then you win. So they challenge people. And you can work out, and we do this in the lecture, you can work out the probabilities of this situation, and you are just slightly more likely than not to get a 6 if you give yourself 4 goes. So he then said, oh, well, I'm a bit bored of this now. What I'm going to do is I'm going to throw 2 dice and try and get a double 6. So how many goes should I allow myself? And he said, well, you're sort of 1/6 as likely to get a double 6 as you are to get just a 6 on its own. So instead of 4 throws, I'm going to times that by 6, cause to sort of, invert the numbers. And so I'm going to give myself 24 throws. And by the same, by this reasoning, it's going to be fine, and I will still be on balance more likely to win. But it didn't seem to work out like that. And he got quite cross about it, saying, well, this means all these mathematical rules are just silly because it's not working. And so he asked a friend, and that friend asked another friend, and the second friend in the chain was the mathematician Blaise Pascal, who is well known for many things, but he was a great mathematician. He was actually born in 1623, so this year that we're recording this podcast in 2023 is 400 years since he was born. And Pascal, in turn, raised some of the questions that Gombo had asked him. It wasn't just that one. It was 2 or 3 questions of probability in gambling that he was struggling with. He discussed them with another very well-known mathematician, Fermat, of Fermat's last theorem fame. And so those two had a series of letters where they talked about these questions, about the throwing of the dice, why you can't sort of multiply by 6 in this way, what is the answer, but some other questions, one of which is called the problem of points. And in doing so, in having this discussion, in which they both actually themselves, made a few little mistakes and then corrected them and worked them out together, they laid really the foundations for the whole of our modern understanding and thinking about probability as a mathematical thing rather than just rules of thumb, heuristics, and this seems to work. They actually laid down some of the rules and worked out what was really going on, and that set in train really our understanding of probability.
What, in your opinion, were they getting wrong, and why were they getting confused?
So one of the big difficulties before Pascal and Fermat, but actually quite a lot of people were still making the same mistake that I'm about to describe for a long time afterwards, is thinking about situations that somehow are not going to arise. Now, this sounds a bit odd, but one of the questions that they were discussing was, what should you do if you're playing some game of chance and you have to abandon the game before it's finished? How should you divide up the prize, the kitty that you've agreed on? And
this moves us into the problem of points.
The problem of points.
It's also known as the division of the stakes.
Yes. So you've put some money into a pot and you're playing some game, and it might be, the first person to throw 3 heads, or the first person to get a 6 if you're rolling a die or something. And so you might get to a point in the game where you've been playing for a bit, and maybe one of you has, I don't know, if it's the first to 3 heads, maybe one of you has 2 heads, one of you has got 1 head so far. So the person with 2 heads, it looks like they have an advantage, and they've got less to do to win. The person who's only thrown 1 head's got a bit more to do. You have to abandon the game at that point for whatever reason. And then how do you divide up the prize? So it feels like the person who's closest to winning should get more of that kitty, but the exact proportions are difficult to determine. And the reason for that is, and I can illustrate this with a mistake made by a very famous mathematician, D'Alembert, who said he was trying to work out, how likely am I to throw a head if I toss a coin twice, at least 1 head. So, and he said, right, there's 3 ways you can do it, because you can throw a head straight away, or you can throw a tail first and then a head and you're happy. But the third outcome is you throw 2 tails and then you're sad, right? So of the 3 possible ways this can play out, you're happy in 2 of those ways.
Yeah.
Therefore, the chance of being successful is 2/3. So, okay, fine. The problem there is the thing that doesn't happen. So in this setup, yes, there are 3 possible outcomes. You throw a head straight away and you're happy, or tail head, or tail tail. But that kind of conflates 2 situations. And it's that first scenario where you throw a head and then you're happy, because then you stop. But what you really need to consider is, because those 3 events are not equally likely, throwing a head to begin with could, if you were to carry on, you could throw then another head or a tail. So that's really sort of 2 events that you don't play out to their conclusion. But in order to have kind of an equal chance of all of the things happening, you need to consider those as 2 separate events, just temporarily, even though you're going to stop and not find out whether your next throw was heads or tails. So if you think about it like that, then there are 4 possibilities: heads, 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 tails, tails, heads, tails, tails. And this time, you're happy in 3 of the 4 times, and they really are all equally likely. So the answer isn't 2/3, it's 3/4.
You need to let the game play out.
You need to let the game play out, even though in real life you would stop before you get to the end.
Yeah.
And that is what underlies so many of these mistakes and misconceptions about probability, even by great minds through time, is being unwilling to even have a sort of theoretical situation, because you're not going to actually, that will never happen in real life because you stop the game at a given point. But in order to use an idea of equal probabilities, you have to write down everything that's theoretically possible and then look at the ones that would make you happy.
And this has far-reaching consequences in today's world, in sport.
Yeah.
In cricket. Could you expand a bit on the Duckworth-Lewis method? You mentioned it in your lecture, but this is your opportunity to talk a bit further about it because we have the time.
Yeah. So Duckworth-Lewis it's been quite controversial because sometimes it predicts things that people don't feel might be the real outcome. But it was created, this method, it's a way of saying which team would have won had you not had to abandon the game because of rain. And in Britain, sadly, that happens quite often. And also with its cricket games, if you're not familiar, they do last a long time. I mean, they last all day. I mean, some cricket games last 5 days. You can have 5-day matches with each side coming in twice. It's probably the only mainstream sport that has tea breaks, I should think. Very English.
Very English, yeah.
So when rain stops play and one side, needs to get, you have to, when you bat, you get runs, and so that sort of points for you, the batting side, and then the other side is trying to get rid of you by getting your players out. So you might have a certain situation where, there's only 3 players that are still to be got out, and they need to make a certain number of runs in order to win. So both sides can win, and it's what's more likely to happen. And Duckworth and Lewis did essentially a massive data analysis of games that had occurred, cricket matches that had been played over time, and looked at, at a certain point in play, 5 hours in, with 1 hour left to play or something like this, what was the eventual outcome? And then they did a kind of analysis of that and worked out the probabilities based on that analysis of all of these games that happened. If we have to stop at this point in the game, who's going to win? Historically, who would have won? And so it's using probability, but based on all this data that they'd gathered. And this method was then used to deem a winner in these matches. And of course, then obviously, if you're deemed to have lost, of course you're not going to be happy with that. So it's quite controversial. In some cases, it's fairly clear if you've only got to get one more run to win, and you could have carried on for another hour, then yeah, fair enough. But in other cases where it's a bit closer, there was always a lot of discussion about, I don't think, this is a different situation. And it's quite a challenging bit of data analysis to do, because you've got all these different factors at play, where the teams are playing, which team is the home side, all of that stuff comes into play. And of course, it's probability, right? So you can't ever be certain of what the predictive method is. But this is a very much more complex and challenging problem of points, really, than the early ones. But it's the same philosophy exactly of we've had to stop the game partway through. What's the outcome likely to be?
But it's interesting because, as you said, the way that they fix this problem is they look at the averages of all the games that have been played before.
Yeah.
And it's an interesting psychology because it sort of ties into the lottery,
Yes.
how people play the lottery, because
Yeah.
in some ways people wrongly play the lottery by looking at all the games that have come before. And I mentioned to you before we started recording, interestingly, how people shouldn't be doing that with the lottery, but it's how people bet on, let's say, for example, football.
Yeah.
Is that, let's say, for the sake of argument, Liverpool have played 25 games, and in all those 25 games, they haven't scored more than 2 goals. It is not unreasonable to bet on the fact that in the 26th game, they will not score more than 2 goals because they haven't done it before. Now, that's slightly different because what you're doing is you're basing it off the fact of human beings because humans are playing football.
Yes.
And there's a reason why they haven't scored 2 goals before, because they may not have a good striker, there may be this, there may be that. There are lots of different factors that come into play, which means that your bet is more sensible than 6 having not come up for the last 4 or 5 years in the lottery. So 6 must be due to come up in the next thing.
Yes.
So it's an interesting way of thinking about things.
And it's, you have, in those kind of sporting situations, it's the opposite of the lottery because the lottery balls do not have a memory.
No. As you
But
said,
you can observe the form of teams or players, and you can make deductions because these are not, game 26 is not independent from, statistically, games 1 to 25.
And two facts that I know is that the fact that 1, 2, 3, 4, 5, and 6 is as likely to come up in the lottery as any other combination.
Yes.
And as you mentioned in your lecture, a bit of a spoiler, but 10,000 people play 1, 2, 3, 4, 5, and 6 every week on the lottery. And if they were to win, they would have to share that. But I think possibly they're playing as a sort of point proving exercise. Maybe they know this.
I think they know. I think what's going on there is they are pleased that they understand that these picking any set of 6 numbers, all sets of 6 numbers are equally likely to come up. You've got a 1 in 45 million roughly chance of that particular set of numbers coming up. Now, we as humans, we can notice that 1, 2, 3, 4, 5, and 6, they form a pattern, but that does not, they are just as likely to come up as any other collection of numbers, because they are chosen randomly. And again, the way the lottery is drawn, the fact that 6 has come up has no effect on whether then 5 will come up and then 4, 3, 2, or 1. So the pattern spotting that we externally as humans are doing does not affect what comes out. So those people who are doing that, they are, well done to them that they know that that's true. But of course, the problem is if you actually are buying a lottery ticket because you hope you're going to win the jackpot, you would be gutted if you won the jackpot of whatever it was, £10 million, and then had to share it
with 10,000 people.
10,000 people. So
it touches upon an interesting part of the way that we think is that we want to see patterns in everything around us because it means that it makes sense. So obviously, what is the meaning of life? Why are we here? Those kinds of questions, those unanswerable questions. People want some kind of sense to them, and they want to see that we as humans are in control of things. There was actually an instance in Monte Carlo in 1913 when the ball fell in black on a roulette wheel 26 times in a row, which is 66.6 million to 1 to happen. Gamblers obviously were getting very frustrated about this, and they were betting against it, and it kept on happening, and they suspected some kind of foul play. And it's just an interesting thing that, we instantly go to that as something's happening, something's going on, we're being tricked, when actually that's not the case at all.
Exactly. And there have been other cases. I mean, that's a brilliant example, because if you think how many roulette wheels, how long have they been going, how many sequences of 26 balls have there been in the whole history of roulette? Lots and lots and lots. millions. And so a 1 in 66 million chance
Yeah.
actually by this time is quite likely to have happened at least once.
Yeah.
Because we've had so many goes at doing this. So yeah, we should be surprised if something like this hadn't happened. And if we think about the lottery, there are several cases actually, where a particular set of numbers has come up one week, and then the exact same numbers have come up the next week. Like more than one instance of this. I think there was one in Bulgaria in the 1990s that I remember. And of course, when that happened, people were saying, well, there must have been a malfunction in the machine. It's rigged. It's like, what's going on? But no, if you think again about the number of lotteries there are in the world every year and how many times we do this process, then yeah, that 1 in a million shot actually is quite likely to have happened over the course of all this time. We can't predict when, but it's likely to occur.
What's also interesting, I've on doing some research into gambling and the lottery seeping into trying to get younger people involved in playing. Obviously, there are laws against, you have to be 18 in the UK to play the lottery. But I found it in the video game world with loot boxes. So there are several video games that use loot boxes, which is basically an award. You get an item, but it's random, and the rarity of the item is also random. So you can buy loot boxes for particular money, but what you get could be something very common, so something not worth very much, or something incredibly rare, so something worth more. And they've come under some scrutiny from governments because they are akin to gambling and they're aimed at the youth. So now some games use a special pity timer mechanism that if the player has opened several loot boxes in a row without obtaining a high rarity item, subsequent loot boxes will improve the odds of a higher rate item drop.
So isn't that teaching the wrong lesson?
It's considered to feed into the gambler's fallacy, since it reinforces the idea the player will eventually obtain a high rarity item after only receiving common items from a string of previous loot boxes. So just to mention that it's now seeping into our into the video game world, which is obviously aimed at younger people. Which is a shame.
And you see this not just in video games, but if you're in an arcade, the machines there, which are, essentially they're random, but what they do is they are expressly built and designed so that a win is shown to everybody. There's noises, there's lights, it's very exciting. And so kind of people who are nearby will be made aware of every win, but what they're not seeing is the silent losses that keep on happening. So again, you get this sort of distorted perception of your likelihood of winning because of the big hoo-ha that happens when you do win.
Which is very evident on the floor of casinos, especially, like you said, when someone wins, it's a huge thing, and you hear it wherever you are on the floor. You do hear it, and it's a sort of mechanism to get people to think, I have a high chance of winning. Also, the fact of when you're on slot machines, if you are on not all games, but on some games, if you need to get 3 of the same symbol in order to unlock free spins or whatever, you get the first 2, and the third one comes over very, very slowly to sort of think that you're just about to get it, you're just nearly there, and so in order to put more. So there is a dark side to it. Towards the end of the lecture, you mentioned 6 ways to maximize your chances of winning the lottery. One of them I won't go into all of them because we want people to watch the lecture, but one of them you do mention, maximizing your chances of winning the lottery, is play a different lottery. Don't play the UK. The UK is 45 million to 1 to win, but it's played. There are other lotteries all over the world, and Italy is 622 million to 1 to win. And I'm not sure of the exact figures, but I understand that Italy and the UK possibly have very similar populations. So do you know why Italy's lottery is a lot harder to win than the UK's?
I think, the design is is different, the choice of why that particular design and why they want or chose those to be the odds of winning the jackpot, I'm not sure. But lotteries have different components. So one thing I didn't talk on as much in the lecture, which is there's the jackpot, but then there are other prizes that you can win.
Yeah.
So in many lotteries nowadays, more or less all lotteries now, it'll be pick some numbers out of a selection, and then if you match 3 numbers, you get a small prize. If you match 4 numbers, you get a bigger prize. There are a lot more ways to get 3 numbers correct out of 6 winning numbers. How are you going to pick that? If you know what the 6 winning numbers are going to be, well, after the event, there's one set of those 6 numbers. So that's your one way of doing it. But in any collection of 6 numbers, there are lots of possible choices of 3 numbers to get. So there are lots more ways to get 3 numbers out of a particular 6 than there are to get every single one of them right. So there's many more ways to get 3 numbers out of the 6 you choose than there are to get 1. And if you work out, and we talk about this a bit in the lecture, but if you work that out, it's about one chance in 96 of matching 3 numbers. You only win £30 though for doing that. So
it's reflected in the money that you win.
So you're not going to get rich. Different lotteries have different prize values for getting 2 right, getting 3 right, and so on. Then they have gimmicks like a Powerball or a Super Ball that if you have that or you don't, it changes the amount of the prize. So depending on how big your choices of numbers and how many numbers you have to select, if you're choosing 5 numbers out of 40, it's easier to get it right than if you're choosing 6 numbers out of 90. So in the Italian lottery, which is probably I think it's the one with the highest odds of the lowest odds of winning, winning the jackpot in the world, which is like 600 million to 1.
Yeah.
And of course, what happens then is people don't win it. I mean, you have rollovers, and so prizes can grow very big. And at some point, then there's a question of if the rollover gets so huge, even though the odds of winning are so small, should I try and buy all the ticket, like one of every ticket? Because then I'd be guaranteed to get, and that is an interesting question. And
this has been attempted, and we won't go too much into it because we want people to listen to the lecture. Because you mentioned a specific example of someone doing that for the Irish Lotto.
Yes, and we'll
successfully.
So we'll see. I'll show you how that works out in the lecture. But just every so often, there are particular lotteries and particular scenarios, and I think one I don't talk about in the lecture is, I think there was a lottery in Massachusetts where some postgraduate students realised that if the circumstances were right, and the circumstances were that in that particular lottery, if there was a rollover for enough time, then they said, okay, we can't have any more rollovers. We have to award the prize this week. So if no one gets the jackpot, what we would do is make all the smaller prizes actually more. So instead of like getting £30 for matching 3 numbers, now you're going to get £90 or something.
Yeah.
And at that point, then you can sometimes guarantee yourself to win. Because if the chance of matching 3 numbers, let's say, is 1 in 96, like we said, maybe it's a 1% chance just for the ease of calculation. And if each ticket is £1, but you're going to win £150 for doing it, then you can see if you buy one of each potential set of 3 numbers, then it's worth your while to do it. So you could work out, it's a lot of work and calculation to realise that there's a chance of doing this, and then you have to constantly monitor. So it's a rare thing to have a chance of being able to do this, and it's only very specific kinds of lottery where that's even possible.
But these examples have been tried before, but they're usually fixed, aren't they? So once someone has proven that you can get round certain aspects of certain lotteries in the world, then it's looked at and thought, we need to change the thing.
Yes, exactly.
I think it reminds me of a good roulette strategy that you also touched upon in the lecture is double your bet on your losses until you win.
Except if you're your 1913 Monte Carlo.
Exactly, but it's interesting. It struck a chord with me because I actually tried to do that when I was must have been 19, maybe 20 years old at university. I had a friend of mine who had made me aware of this and thought, this is great, we can make easy money. I think we went on an online betting website, I can't remember which one, and we did exactly that. So we carried on and on and on, and I think we made a profit of about £20. I'm not sure, I can't remember what we were doing. I think it was 50p's or £1 we were doing each time. And then I think something kicked in the software of the game, the algorithm started to realise what was going on, and we lost everything. So then following a particular point, it made us lose and we lost all of it. So as you said in the lecture, this could be done on a very, very large scale, but of course to do it on a very, very large scale and to make, I don't know, some money, you need to start with a large amount of money.
Start with money and have lots of resources, because you've got to be able to cope with the scenario, the 1913 scenario, right?
Of everything.
Can you double your money 26 times?
But actually, at the end of it, your profit is incredibly small, isn't it?
Yeah. Because so you can sort of think this through and say, if I bet £1 and lose, and then I double it to £2 and then double it to £4, and maybe then I win, and the winning counts, maybe it's doubling your money. So then you come away, you've won £8, but all the stakes you've put in is you've lost £1, you lost £2, and then your £4 bet was, so actually the amount you've put in is £7 and you've only won £8.
Which again,
and you forget that along the way. You remember that, I doubled my £4 to 8, but you forget all the things you've lost before. So you forget all the lottery tickets you've bought for 10 years, and then you match 4 numbers and you win £1,000, but 10 years of lottery tickets.
Exactly. It made me think of scratch cards, of people winning £500 on a scratch card.
Yeah.
When I see that in the paper, or when I see a story like that, I always think, well, how much have they actually spent to win that £500?
Yeah, exactly.
If you're buying a scratch card regularly, some people, not everyone, but I would say some people buy scratch cards maybe one every day, or maybe 2 or 3 every week. To finally get that winnings, they've probably spent more than £500 in order to get it. So it's a mug's game. Yeah, that's what my dad has always told me.
No,
is playing the lottery is a mug's game. And as you rightly and very responsibly mentioned in the lecture, never bet what you can't afford to lose.
Yeah, exactly.
So you can play and have a good time and have a bit of fun, and £1 here, £10 there. Yeah. But if you're betting £10, be prepared to not see that £10 again.
Exactly.
So that's the trick of it. What are the chances that you've picked a series of 6 numbers that no one else has picked? Can you try and maximise your chances that you have a unique set of 6 numbers every week, so you don't share the jackpot when you win? So this ties into sort of trying to beat the system, or trying to put yourself in the best position over the millions of other players who are playing the lottery. Is there any? Could that work? Does that make sense?
So there's 2 observations really. The first is, as we've reminded ourselves, the lottery balls do not have a memory. So any analysis you do on what happened last week is not going to help you know if there's any numbers that are more likely or not to come up. Every set of 6 numbers is equally likely, but it's a different kind of analysis that you can think about, and that's almost about human psychology, right? We've mentioned already that you shouldn't pick the numbers 1, 2, 3, 4, 5, 6, because lots of people do to kind of prove a point. But there are other numbers that people pick. Now, you said right at the beginning that there's a study done that says people are less likely to pick numbers that have come up previously. So depending on how big that effect is, you could consider, not because the mathematics says those numbers have a different probability of coming up, but because you want to avoid sharing the jackpot. So actually the only thing you can really do is to try not to share. We don't want to share the jackpot, so we don't want to pick numbers everyone else is picking. Now, what do people do? We're all superstitious, we all have our things. I remember when the first lottery came out, and my parents, like everybody, seemed to be buying a lottery ticket because it was a novelty. And the numbers they picked were based on their birthdays, and their wedding anniversary. And so when you're doing that, the numbers that are more likely to come up then are the days in the month, which can go from 1 to 31. So you probably are likely to get more of those sorts of numbers are getting picked than higher numbers that cannot be a day in the month. So that is a potential thing to think about. If you have a sprinkling maybe of numbers that are higher than 31, these are all, in some sense, you could say this is statistics because you're looking at what people actually choose. This is not, I repeat, it's not about numbers that are more likely to come up.
No.
It's numbers that are more likely that other people will choose.
Yeah.
So it's sort of human nature meets statistics here.
Your strategy is not trying to essentially beat the machine. Your strategy is trying to beat other humans.
Exactly.
Which is more sensible because we're all human, and it's basically trying to predict what other humans would do in order to win.
Yeah.
Which is interesting. We'll move on to our feature of unanswered questions from our audience. So politicians like to talk about and extol the virtues of STEM subjects, science, technology, engineering and maths. And I wonder if Professor Hart, who has written about the links between maths and music and maths and literature, is happy with this classification of her subject.
Yeah, it's a really difficult one.
Okay.
Maths is in many ways a very fortunate position in that it's incredibly useful in everyday life. It's incredibly useful for science and technology and all of these things, because maths is the best way that we have to understand and explain structure. The universe has structure and pattern. Maths can encapsulate that in equations which we can try and solve. And so if you're trying to understand the universe, if you're Isaac Newton, you come up with the equations that govern gravity. That maths is a natural tool for doing that. It's useful for engineering and all of these subjects. So it's got incredible utility and it's vital for science because of that. However, as well because of its brilliance at dealing with pattern and structure, it's really important and relevant to other creative subjects. So I think of mathematics as a creative thing. I think of what I do when I'm exploring and playing with shapes and patterns and symmetries. That feels like being creative and thinking creatively. It feels like an artistic subject. And you can see in our other artistic subjects like music and literature and poetry and art, there are structures and patterns there, and that's what mathematics is so good at. So for me, it has these wonderful links with these what we think of as the creative arts. And that I, as a mathematician, I sort of feel naturally, I feel like a more part of that arena. And it doesn't mean that I don't care about science. I find science very interesting, but I don't think it serves anybody to put maths in a box in that way, because it goes across everything. And so, of course, it's very useful, but that's not all it is. It would be like if you said that the purpose of art was to do technical drawing. I mean, yes, if you want blueprints, or you want to build a building, you need a drawing of that. But that isn't what art is for. And in the same way, it's not what maths is for in my mind. Maths is just, we do it for the sheer joy of it. And so it links to lots of other things. But I don't like anything being put in a box in that way.
The questioner mentions politicians in his question, but it seems to be politicized, doesn't it? The STEM, and it's being played as a football being kicked around and something which, like you said, it's pigeonholing it too much.
Absolutely, and I think it also sets up this sort of false dichotomy really between arts subjects and science subjects, and as ever there's finite resources. So the risk there is that then, you stop funding music lessons for kids, and you say, well, because, if you want to get a job in tech, you have to learn maths and computing and stuff, and that I don't want those to be choices imposed upon people. And we do hear the politicians, every so often. Rishi Sunak will give a speech saying we need to teach maths to age 18. Right? He seems to say this every few months. And the people on the ground, the kind of maths teachers in schools who are doing an incredible job with the challenges that they face. There are practical responses to that, which is, right, we already haven't got enough maths teachers, so who's going to be doing this teaching?
Yeah.
But another thing to say is, why, yes, maths is important, but we seem to have somehow we got ourselves into this situation of being in a world where actually a lot of people don't like maths. They will openly say, I was never any good at maths, it's not for me, I'm more of a creative person, which I obviously go, but maths is creative. But there's this, and it's sort of socially acceptable to say that you're no good at maths and to not like maths. And I'm not saying everyone has to be a professional mathematician, but I think it's such a shame when maths has so many beautiful aspects to it.
It's got its branches in so many different industries as well. Like, I think, from my understanding, when I was younger, I think I was just told that where can you go? I wasn't shown the journey that you could have by studying maths at university or making it your skill and your thing. I think I just believed that studying mathematics basically meant that you're going to become a teacher or a lecturer. Yeah. And that's it.
Yeah. Or work in finance.
Exactly. Or become an economist. Yeah. So there wasn't I wasn't told about all these different possibilities. Yeah. And especially with where we're going with technology and AI. Yeah. That's all maths. Yeah. It's, people, the top people who work at these huge tech companies, Amazon, Google, are all fundamentally mathematicians. Yeah. You need to have a basic understanding of that. You
do, but there's also, to some extent, I think even people who would say they don't like maths accept that it's a useful thing. It's just that, unfortunately, for whatever reason, people get to age 16 and can't wait to stop learning maths. And I just feel so sad about that, because I think there are ways that we could show people, some of the exciting things about maths and the way in which, the curriculum has been designed. I think there's lots in it. There's too much in it probably, because what you'd really like, I think, is to play with and explore ideas like you do with music. You don't take 5-year-olds and say, right, we're going to learn by rote all the scales and all the key signatures, and then in 10 years you might be able to play a tune. We just sing songs. But in maths, somehow it's differently done. We do say, right, you're now going to by rote learn all the times tables, and now you're going to learn long multiplication and the column method of addition, and then you'll do long division. And by the time they get to secondary school, perhaps they've forgotten the curiosity and excitement about numbers and shapes.
It's the way they're being taught it.
Which is not the fault of the teachers. I really want to say, because teachers are amazing. I think
it's the curriculum.
It's the curriculum saying, right, here are your SATs. I don't know, why do we make these little kids do exams? I don't know. Anyway, they've got, and they have to do all this stuff, and that's how the schools are funded.
It sucks the fun out of it. It's related in a way, bit of a tangent, but it's related to the way that I studied English. Was the way I was taught to write essays is each paragraph had to have a point, and then you had to describe the point, and then you had to, and it had to be done in that way. Yeah. And I wrote, I was told by my teacher that I wrote a really fantastic, interesting essay, but I was only allowed to be given a D because of the way that it was written, and it wasn't written in the way that the curriculum asks you to write it. So some of my in ways my creativity was kind of beaten out of me, and I was sort of forced to kind of write them in this particular way in order to get the B's and the A's. And I would imagine that relates to maths as well, in the way that the way that it's taught. Yeah, you've got to do this method and this method. You've got to show the working of this exact working. My 16-year-old has just finished her GCSEs, and I was astonished at how much there is on the GCSE curriculum. And what it means is that everyone's just hurtling along. You haven't got time to, play with some lovely ideas in geometry and think, oh, what would this be like in 3 dimensions, and have just fun exploring it, because you've got to go, right, today it's Tuesday, so it's circle theorems, bang, 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 bang. You don't think, why are these theorems interesting? Why do we care about angles of weird shapes inside circles? It's just boom, and you have to, the teachers are great, and they're really trying to give the joy of the subject to the kids, but ultimately they know they've got a week
to do this topic, and you just have to go through it. And I think that's there are ways we could.
And this ties in beautifully to Gresham. So
there you
this
go.
is what we're trying to do.
Yeah.
Is with Gresham, our professor of geometry is the original, one of the original professorships. We have sponsored professorships now, but is one of the original professorships. And I think what we do so well is we take those fundamental principles of mathematics and what you need to know and what you need to understand, but we apply it to real world issues and to things that people can relate to. And I think that's what you do so well. Thank you very much, Sarah, for that conversation. It was really enlightening. And in September, we have you back. Is there anything you can say about your new series for Gresham?
Yeah, so the theme for the coming year is games, puzzles, paradox, and proof. And so we're going to start with looking at, a bit like the lottery, but going into the idea of board games and games that we play, like chess and other games like this, where it's not just chance, there's also strategy involved. And mathematics has a lot to tell us about how we can decide how hard is a hard game. Chess is supposed to be really hard. There's an even harder game than chess out there, which we'll talk about. Can computers learn to do these things? Computers are pretty good at chess. How good can they get at all games? So the mathematics of kind of games and the complexity of games is in there. That moves us on to thinking about puzzles, which are another thing we spend our time doing. And puzzles take us to paradoxes and riddles and mathematical ideas that are confusing but have an underlying grain of truth that can actually help us to find new and interesting mathematics, to explore these paradoxes. And we're going to finish up, because I'm a mathematician, what I do is mathematical proof a lot of the time. Yeah. And we're going to finish up in the year by having a look at my favourite mathematical proofs and what makes them so beautiful.
Thank you. That sounds really exciting.
Great.
And if you want to watch any of Sarah's lectures, we have our YouTube channel, Gresham College, and we also have our website, gresham.ac.uk, where you can see all of her lectures, you can listen to them, and you can watch them. And I look forward to either having you in person in September in our new year at Sarah's lectures, or you can join us on live, as there will be live streamed. Thank you very much for joining us. Thank you.